Welcome back. In this section we are discussing the III-V PV technology and its special applications. In the previous videos we discussed concentrated PV. In this video we will discuss the use of III-V multijunctions in space. We will start this video with a short history of the use of PV technology for space exploration. You will then learn about the special design considerations for PV devices in space, such as the different solar spectrums and the substrate choice. Historically, solar energy has always been the ideal energy source for the space industry. PV technology can provide a relatively lightweight energy source and long autonomy. The same cannot be achieved by any fuel source or batteries. In 1958, the first solar-powered satellite, Vanguard 1, was launched. This satellite had 8 small panels consisting of 6 series-connected silicon-based solar cells. Each panel had an output power of around 50 milliwatts. During these years, space industry represented a safe niche market for innovative photovoltaic technologies. Nowadays, the largest PV power system present in space is the one on the International Space Station. The ISS features 8 solar cell arrays of around 400 square meters, generating an average power of around 110 kilowatts. Since the 90s, PV research for space applications has focused on the III-V and multi-junction devices, which have higher efficiencies and are more tolerant to the radiation environment. As we discussed in the previous videos, III-V multi-junction devices have the highest power output density of all PV technologies. This means that in order to generate a certain output power, fewer models and a smaller surface area is required with respect to other technologies. Additionally, as III-Vs are direct bandgap materials, thinner absorbers are required for achieving certain photocurrents in reference to their indirect bandgap counterparts such as crystalline silicon. This consequently leads to smaller and lighter solar arrays. This is extremely important for space industry since it can cost many thousands of dollars to put a single kilogram into space, depending on the type of mission. A typical III-V triple junction device has a gallium indium phosphide top cell, gallium arsenide middle cell and a germanium substrate, which acts as the bottom cell. Germanium is the preferred substrate because of its low bandgap, low cost and high mechanical strength. However, the germanium substrate is a relatively thick and heavy component that significantly increases the weight of the device. Researchers have therefore investigated the use of different materials to replace the heavy germanium substrate. A promising design, known as an inverted metamorphic multijunction device, takes a different approach. This design starts with a crystalline gallium arsenide substrate. A gallium indium phosphide layer is deposited on top of this substrate, which will adopt the crystalline structure of the gallium arsenide substrate. 3 more III-V alloys are deposited on top of the gallium indium phosphide layer with decreasing bandgap energy. Since the used alloys are not lattice matched, buffer layers are deposited between the gallium arsenide and gallium indium arsenide alloys. Finally, the gallium arsenide substrate is removed through a lift-off technique by using a temporary gallium arsenide substrate. The need for the bulk crystalline germanium wafer is removed. With this design, a lightweight, flexible and highly efficient device can potentially be realized. The weight is not the only space-related design consideration, however. Earth's atmosphere filters out most of the sun's higher energy radiation. In space, the solar cells will be exposed to this radiation, which could potentially lead to the degradation of the solar cells. There are different sources of space particles. Solar wind, solar flares and galactic cosmic rays consist of charged particles such as electrons, protons and ions that interact with the magnetic fields of the different planets in the solar system. There are regions of trapped charged particles called the Van Allen belt that can be modeled so that the radiation can be predicted. Other radiation sources are not so predictable. Solar flares consist of highly anisotropic protons, which lead to sudden proton flux variations. Additionally, magnetic solar storms can create an electron flux in the outer orbits for short periods of time. The materials used for PV in space should therefore have a high radiation resistance. Another issue is the particulate environment, which comes from both meteoroids and man-made space debris, shown here by this artist's rendition. The latter has been increasing strongly over the last years due to the high number of spacecraft launches. Particles greater than 1 milligram are believed to cause severe damage, such as erosion and mechanical cracking of the solar cells. This has to be taken into account during design of the encapsulation layer of the solar cells. A final design consideration is the available solar spectrum in space. Terrestrial solar cells are optimized for AM 1.5 conditions, where some parts of the solar radiation are filtered by the Earth's atmosphere. For space missions, solar cells have to be optimized for a different spectrum. Just outside Earth's atmosphere, this is the AM 0 spectrum. This spectrum has more power available on a short wavelength part of the spectrum. Using a solar cell in space that is designed for terrestrial use can result in a significant decrease of the efficiency. For planetary space exploration, the design gets even more complicated. The available intensity and temperature will change significantly depending on the distance from the Sun. For interplanetary missions close to the Sun, the arrays must be capable of withstanding temperatures above 450 degrees Celsius, while functioning at high solar intensities. Outer planetary missions, on the other hand, require solar cells to operate under very low intensities. For space missions towards Mars, for example, the PV system must be designed in order to cope with low intensity conditions. The AM0 spectrum and the solar spectrum outside Mars is plotted in this graph. We can see that the maximum power has slightly shifted towards the red part of the spectrum due to the interaction with matter in space. The design of solar cells that operate on a different solar spectra is especially difficult for multi-junction devices. For optimal operation, each of the subcells in a multi-junction device should be current matched. But as the device moves further from the Sun, the power available in each spectral range changes relatively to one another. The current generated by each subcell will therefore change to a different degree. This means that the output current of the device will be suboptimal. Now, in summary, we started this video with a short overview of solar cells used in space. You then learned about some important design considerations for PV technology in space. The weight of the germanium substrate leads to innovative design with a temporary substrate. The high energy radiation and space debris demand the use of radiation-resistant materials and special encapsulation. Finally, the temperature and intensity can vary strongly on outer space missions, which is especially challenging for multi-junction devices. I'll see you again in the next video.